So how does a smartphone camera or any other sensor or camera work? Well, the basic physics is that when you have a substance, something like glass, with a high refractive index, when light enters it, it changes direction. It changes direction again when it leaves. The equation for how it changes direction as it goes through a surface is known as Snell's law. If you need to know, you can look it up easily enough. But for most practical purposes, what people do, let's say you want to work out some light from a light bulb shining through a complicated set of glass like this. What you do is, with a computer program, you'd simulate large numbers of rays, and for each ray you'd work out how it bends when it comes in and out. These are called ray tracing software. Sorry, that shouldn't bend like that. And you can use them to calculate how light propagates through any shape of glass or different bits of glass and so on. These are used in computer graphics to get nice images, and they're also used by optical designers to work out for a particular lens or combination of lenses, if you have light coming from one direction, rays, where they would end up. So here's the simplest possible design for a smartphone camera, which is basically you have the object being focused, a friend or a landscape or whatever you're photographing, and there'll be light coming from different places. So for example, this is a friend, that might be their head, and this might be their feet or something like that. If it was a scenery, this might be a mountain range. Then you have, in the simple case, one lens, and assuming the optical designers have done their work right, the shape of the lens, the curvature of the glass, means that light from any one location will be brought to a focus on a plane, so-called focal plane, which will have a detector, typically a charge coupled device, which is a silicon chip which records the photons of light that land on it. Ideally, anything that's in this plane over here, the object plane, any location here, should be mapped to a particular location over there, so all the light from here, no matter which part of the lens it hits, whether it's the top of the lens or the bottom of the lens or the middle of the lens, they'll all be brought to a focus at the same place down here. Now in practice this is very hard. It is actually possible, if you have everything right on the axis of the lens, to have a perfect focus. But if you want also light to be focused above and below and all different wavelengths, you have to bear in mind the refractive index of glass depends on the wavelength. So an ideal camera would bring light from anywhere in this plane to a perfect focus on this plane over here. That's very, very hard. Real lenses cameras don't use a single lens, they use multiple lenses. Here, for example, is a graphic of the lens in the iPhone 6, and what you can see is there are a lot of lenses in here, all made of different sorts of glass and all moving back and forth in complicated ways, so that you can get a sharp image of every point here onto the detector over there. Now, the one crucial thing we're going to need here is to work out where on a detector light from a given direction will come through. So let's say you've got an angle here, theta. If you've got, say, a head and a foot theta apart, where will they land over there? And the trick you use for doing this is that a ray going through the middle of a lens, like this ray here, or this ray there, is undeflected. Why? Because near the middle of the lens, the two sides of the lens are parallel to each other. So any light coming in will get bent when it goes in, but then will get bent equal and opposite when it comes out, and so it'll end up parallel to and very little displaced from where it came in. Likewise, light coming in from this direction will get bent and then get bent back again. So you can more or less, to high approximation, treat a light ray that goes through the center of the lens as going straight through, and that's what we're going to use going forward.